Okay, let's solve lots of equilibrium problems. This is Dr. B, and let's go. Let's define chemical equilibrium as a state of reversibility. It's not when a reaction is stopped, but it's when the rate of the forward process is equal to the rate of the reverse process. Let's write some expressions. For those, it's always the products divided by the reactants, their concentrations, or if it's pressure, their pressures. The coefficients become exponents, and we only deal with systems that are homogeneous. Therefore, we're going to omit in general solids and liquids. For this one, the concentration of ozone squared divided by the concentration of molecular oxygen cubed. See? Products on the numerator, reactants denominator, coefficients become exponents. For this reaction, we're going to have to take, nothing gets excluded. Oh, yes, something do. The iron's a solid, so put a big cross through that. And KEQ simply equals the concentration of the product divided by the reactant. That should be an exponent right there to the fifth power. That would be a big change. For this decomposition reaction, they have three products. Everything's in solution, so this one's squared divided by that one. There it is, ammonia. KEQ equals concentration of ammonia squared times the concentration of carbon dioxide times the concentration of water, since it's a gas, divided by the concentration of the ammonium carbonate. That would have to be heated awfully hot, by the way, to make that salt a gas. For silver nitrate decomposing, everything's aqueous, that's fine. So although this is a net ionic equation, we don't let that worry us. We simply have those two ions as our products, each to the first power, divided by the concentration of this silver nitrate, and that should give us the equilibrium constant there. Okay, here's a longer problem. We've got some nitrogen dioxide, which is dimerizing into dinitrogen tetroxide. It's got a nice equilibrium constant. They give you a bunch of data and say, under those conditions, is the system at equilibrium? So why don't we just set up KEQ, it's going to be that over that, and see what number we get and compare it to 170. If it's less than 170, things will shift to the right. If it's beyond 170, that's a system that cannot hold because the equilibrium constant says, oh, you know, that's too much, and it'll shift to the left. We call this comparing Q with K, where Q is the observed equilibrium and K is the equilibrium constant. And in this case, it's 375. Those should be exponents. That's too high, right? That is too high, so it will shift to the left. The nitrogen dioxide concentration will increase until it hits 170. Here's a reaction of carbon with carbon dioxide to make 2 molecules of carbon monoxide. That's interesting. And it's at 700 degrees. Fine. Let's find K. I guess we better set up the equilibrium constant expression. This does get omitted. See it? Chop it out. So it's going to be CO squared over CO2. Include those concentrations. In this case, you'd have to do mole per liter. Watch out because it's 2 liters. This is not a 0.1 molar solution. It's only a 0.05 molar solution. All those, their molarities will be half the number of moles since it's a 2-liter flask. K is going to be CO over CO2. Plug in. Don't forget to square the carbon monoxide concentration, and you have a pretty lousy equilibrium constant if you're trying to move forward. Here's another one. Calculate K. They give you the size of the flask. Once again, it's 2 liters, so this is 0.05 molar with respect to carbon monoxide. This is the same chemical reaction, so we're going to set it up identically. We've got some different numbers. Same thing. Don't forget to square the top. And once again, it's the same thing. Isn't that interesting? All they did was change the concentration of carbon, which doesn't matter. It's not part of the equilibrium. And then they pointed out, why are they the same? Well, because carbon doesn't really play a role in the equilibrium since it's not mixing homogeneously. Number 39, a mixture of carbon monoxide and chlorine are placed in a flask. Here's some concentrations, and they do not, so we got some initial concentrations, fine. They tell you what the change is for the product, right now Cl2, one of the reactants, when we're at equilibrium. So we want to find the concentrations at equilibrium. This is our first ice table problem. They're giving you some initial conditions before anything happens. They're telling you once you hit equilibrium, they only give you one of the things, which doesn't seem like enough, but it is because of the ratio, 1 to 1 to 1. So for every molecule of chlorine which gets consumed, one of these gets consumed, and one of those formed. It's best to do this using a nice accounting procedure, so we make an ice table, right? Here's what we know initially. There's the products carbon monoxide and chlorine. We have nothing, no phosgene yet because this thing has not begun. The change they don't give you directly, but they imply it since they told you that chlorine went down to 0.003 molar. So we can calculate the change right there. That's what you do next. Now for the big aha moment. If that's going down by that much, so must this due to the 1-to-1 ratio. Products always form. This must go up by that much. So I'd put a nice big double arrow right there to tell you that's where things are changing. Products always increase. Reactants always decrease. We now have, by virtue of simple accounting, our three numbers that we need. Plug them into the equilibrium constant expression, and you find that we get a nice strong equilibrium constant of 141. Those are ice table problems. We'll be doing lots of those. The equilibrium constant for the reaction of carbon dioxide, which is decomposing, is terrible at 1000 K, 10 to the minus 12th. Let's find the equilibrium constant for a different reaction. And what is that reaction? Well, it looks like things got flipped over. See how we have CO as a reactant? Therefore, there's a rule for that. We're going to flip this thing over and take the inverse of that K value, making it suddenly extremely high. But that's not the only change. They also doubled everything from 2 to 1 to 2, down up from 1 to 1 to 1/2. Therefore, when we double everything, we go up an order of magnitude, and we'll square that K value. So the original K inverted and squared will give us the new K, which is 2 times 10 to the 22. Huge difference. Here's another case where we can combine reactions to bend to our will. They tell you what the one they want is. This is tin 4 oxide reacting with carbon monoxide. We want to know what its K value is. We don't have it, but we do have the K value for a couple of related reactions, and these are always set up that if you flip them over, double them, multiply them, etc., you will end up with the desired reaction. So what you do is see if it's on the right side and see if it needs to be multiplied. So I do like the fact that the given value is tin 4 oxide and it's not multiplied by anything, so I'm just going to keep this one, assuming everything works out. But for this bottom one, where is hydrogen? Well, I guess it'll be canceling. The only way it can cancel is if we flip it over. But if we flip it over, it's not enough. So I'm guessing we're going to flip this one and double it. So we'll take 1 over K squared for this one. Is that really true? I think so, right? We want carbon dioxide to be a reactant with a coefficient of 2, but we have it as CO as a coefficient of 2, but we have it as a product. So we got to flip it over and we have to double it. So we'll do 3 things. First, we're going to invert this K value. Second, we're going to square it since they were doubling everything, so you square its K value. And then since we're combining these two, we'll then multiply this K value by the new one. That's a mouthful, so you definitely want to write things down nice and clean. So there's this one being kept as it is. Here's this one flipped and squared, and you should add things up nicely, see that everything that needs to cancel cancels, then just do the math at the end, and you end up with a K value that's pretty good, 13.7. Okay, that's a bunch of equilibrium problems.